So thank you. Thank you to the organizers for the invitation to speak here. I was invited to talk about diagrammatics and categories, and there's a lot to say. And so I opted to kind of give you 5 different talks. Now, they're not going to be completely disjointed, of course. They'll have to sort of build on each other. But what I was thinking was that it's sort of these sort of diagrams and categories kind of make the most sense if you see them arising naturally in a particular context. And so rather than try to generalize that as much as possible, I thought I would give you hopefully something like 5 different examples of categories that have diagrammatics, and you can do the generalization yourself. Before getting into, so today I'm going to talk about Frobenius algebras, okay, as our sort of starting example of a place where we have meaningful diagrams without sort of needing to bring in too many more adjectives. But before I talk about any of these things, I wanted to give some references. So the context that all of this is happening in is tensor categories. And so if you were here last week, you saw Dimitri's excellent mini course, and you should be comfortable with those. The Eddinghoff, Jalaki, Nikšić, and Ostrich book called Tensor Categories is the Bible in this field, right? Like anything you want to know about tensor categories is probably in there. So it doesn't actually have very much diagrammatics in it, though. So for that, there's a recent book by Chris Hunin and Jamie Vickery called Categories for Quantum Theory: An Introduction, which is really well done and has a lot of beautiful diagrams. And they're particularly focused on the cases that they care about in quantum contexts. So it has that particular point of view, but what that means is that it's a slightly shorter book than if they were just kind of considering everything all at once, a little more focused, probably particularly interesting to people with more of a physics bent. Okay, but then also there's a paper of Peter Selinger from 2011 called A Survey of Graphical Languages for Monoidal Categories, which is a good starting point if you don't want to start by reading an entire book. If you have a little bit of background already, this is a nice attempt to really put these diagrammatics on a rigorous footing without spending hundreds of pages. Okay, but what I'm talking about today, Frobenius algebras, most of this material comes from the Hunin Vickery book, or Joachim Koch has a book, Frobenius algebras and 2D topological quantum field theories, and he also has an article that summarizes the book, which is a good place to find this stuff. Okay. And now I'm really glad the way the schedule for this week worked out, because I'm going to start with the question of what is a TQFT, and if we had the third mini course this week, if she had already given her first course, this might have been completely trivial and covered by then. But I get to do the introduction to this. So topological quantum field theory refers to a machine that takes in an n-dimensional manifold with boundary and probably some other adjectives, which I'll get to, and gives you back some sort of linear map on vector spaces. Okay, and so in particular, that's not a very rigorous formulation. So maybe I'll say that this is a monoidal functor. The monoidal category of cobordisms to the monoidal category of Hilbert spaces. Okay, and now I have to tell you about these 2 categories, right? So in the cobordism category, our objects are closed, compact, oriented, and manifolds. No. n-1 manifolds. And then our morphisms are n manifolds. So a morphism from an n-1 manifold to another n-1 manifold is an oriented n manifold, call it M, with whose boundary is these two manifolds, lower dimensional manifolds that it's mapping between. Bless you. Okay, so for example, if n equals 2, then we could take maybe sigma to be a single circle, sigma prime could be a pair of circles, and then any manifold you can put here in the middle is a morphism between them. Okay, and the memorial category structure comes in, so composition, if we went from sigma to sigma prime and then to another sigma prime, we would just glue the two manifolds together along their common boundary. So composition is gluing. Okay, a question for you. If composition is gluing together along a common boundary, then what should be the identity? What should my unit object be? Empty? Unit object. Yes, I said the wrong thing. Sorry, what should the unit morphism be? The identity morphism.
The cylinder of the boundary. So
yeah, that's right. So if I have a specific boundary, then I take
the cylinder, maybe.
2 copies of that and make a cylinder between them. And of course, then if I glued that onto something else, up to a little bit of topology, it would be the same thing. Okay. Okay, so that's my identity morphism. But I also have a tensor product. Okay, and the tensor product is disjoint union. Okay, and so this is just the easiest tensor product ever. If I want to take the tensor product of a circle with a circle, I put a circle down next to a circle, and that's it. If I want to take the tensor product of 2 morphisms, I just put them down next to each other, don't let them overlap, and I'm good. So yeah, so the unit for this is the empty manifold. Okay, Simon?
sorry, one question back to morphisms.
Mm-hmm.
Isn't there something need to like take care of the orientation so that the domain and codomain have to be taken?
Yeah, probably, right? So if M is oriented, then it should induce an orientation on these, right? And yeah, it should be clear which is your domain and which is your range just from the orientation. Yeah, I'm going to skip the details past that point, but
For a morphism is up to the diffeomorphism, right? Or
yes, yes, that's right. So whatever sort of manifolds you're working with, you know, I'm just working with topological manifolds here, right? So up to diffeomorphism, but if you wanted to put some more adjectives, then you might change your destination over here, and you might consider a different notion of equivalence then.
Is your target hill because things are oriented or because of physics?
But because of physics, yeah. In just a minute, yeah, let me just really quickly write down what Hill is, and then I'm going to tell you an analogy I don't completely understand that will account for that. So, okay, so I'm going to use recall, one of my favorite math words. It means I'm not actually going to define this, but we're going to agree to pretend that I have. So Hilbert space is a vector space with a complete inner product, okay? Meaning that we have an inner product and that limits exist, all that good stuff. So Euclidean space, everyone's favorite example. Finite dimensional Euclidean space, everyone's favorite example of Hilbert space. If you want infinite dimensions, then you have to be a little bit careful. Okay, and so the category of Hilbert spaces has Hilbert spaces as its objects. And the morphisms of this category are bounded linear maps between Hilbert spaces. We have composition of morphisms, which is just function composition. And the usual tensor product of Hilbert spaces. Okay, and so it's a lot like vect, okay? We're just adding in this complete inner product, and our linear maps have to be bounded.
Are we allowing for infinite dimensional Hilbert spaces here?
Yes,
Okay,
I have not specifically ruled them out.
thank you.
But we don't really need to, right? Because the image of your TKFT, like everything's gonna be fully dualizable, right? So
Probably.
probably
Yeah.
everything's gonna end up being finite dimensional.
I mean, I'm actually not going to talk a ton about TQFTs beyond here.
Okay.
Yeah, okay. So why do people think about TQFTs? Okay, other than the fact that we like functors. And I found the answer to this in this paper, which where the author specifically says, I'm not a physicist, but this is how I understand it. And so on the one hand, I am also not a physicist, so this is the right answer. For me, on the other hand, if there are physicists who want to correct me or say something more accurate after I've said this, you should definitely do that. But okay, so the idea here is that a TQFT can be a toy model of quantum gravity. Ooh. Okay. Why? Why is this a sensible thing to do? So if we think of our closed manifolds as corresponding to space, then our cobordisms, our morphisms, give us a notion of space-time. And over on this other side, where we have Hilbert spaces and bounded linear maps, you should think the Hilbert space as giving you a state space for your quantum system, and linear maps as your time evolution operator. Okay, and so why is this quantum gravity? Well, as I understand it, you have both something that's happening on a large scale, okay, something that's happening on a global scale over here. And so that's the gravity side of things. And then you're mapping to a sort of quantum system, right, where you have something representing state spaces, things representing time evolution operators. I cannot answer any further questions about the details of this, but if you have anything to add, if anyone here wants to say anything about this analogy that I've quoted, now would be a good time.
Yeah, I think it's a toy model because you don't have the metric, right? It's just topological, this thing.
Yeah, very much
Yeah, because
toy.
gravity
Definitely.
actually has a metric. Yeah.
Yeah.
Motivate this by writing down action functionals on these manifolds. And these have to be ones that depend only on the topology and that elements. That's not very natural. Yeah, because it doesn't depend on topology, everything. There's no dynamics or positions on any of the manifolds.
Yeah. Okay, so let's change tracks a little bit now and talk about what this talk is actually supposed to be about, which is Frobenius algebras. Okay, so what is a Frobenius algebra? So the context here is that we start with C, which is a monoidal category, and it has, of course, the monoidal structure given by a tensor functor, a unit object, and unitors and associators, which aren't super important for what I'm talking about today, so I'm just going to gloss over that part. Right, and so we've already seen many examples last week in Dimitri's mini course. The cobordism category and Hilbert spaces are also an example of this. Pentagon axiom, et cetera, et cetera. But so in this context, a monoid is a triple consisting of an object and two maps, and I'm going to draw the maps graphically. Okay, so we have A, which is an object in the category. And now I'm using this picture to represent a morphism that takes in 2 copies of A and produces a 3rd copy. So I'm using the optimistic convention here, where we read our diagrams looking upwards. So what we have here is 2 copies of A coming in and a single copy of A coming out. And then we have a second morphism that looks more like this. And this one has, well, a single copy of A coming out, but it seems to have nothing going in. Okay, and so like we had over here, where our unit was the empty set, over here, when we have 0 strings, we're going to think of that as our unit object. Okay, so if we're given this data of an object and maps that fit into this with the following properties, then we have a monoid. And the properties that we require are, let me draw the pictures, and then everyone can, while I'm drawing them, see if you can interpret them. And I'll tell you the interpretation in just a minute. What is this first equality of morphisms saying? Associativity, yes. Right, so if we have 3 copies of A coming in, it doesn't matter whether we group the first and the second, or the second and the third first, and then do the remaining grouping, we get the same answer. And what are we saying over here? So this is saying something about how the unit and multiplication interact, right? So what we have right here is the identity morphism on A. And what we have over here is a map from, well, really from A tensor, the unit to A, and from the unit tensor A to A. Okay, and so this is saying something about how these 2 maps interact with each other. Okay, and that's all you need to be a monoid. And now a comonoid is exactly the same thing as this, but we draw everything upside down. Okay, right, so for a comonoid, we'd have a triple of objects, and then instead of a multiplication, a splitting map, and instead of a unit, a co-unit. Okay, now I think I've sort of implied this already, but since this is a course about diagrammatic calculuses, I feel like I should be explicit about it. So I'm just going to write down how we read these diagrams. Okay, so with this sort of picture, every string is labeled by our monoid A. Okay, and what I'm going to call invisible strings are labeled by the unit. Okay, meaning that, you know, if you have basically the only way this happens right now is with this piece, right, with this unit morphism. But if you ever need, you know, to write a unit down, you're allowed to write down as many units as you want without any reference to what's actually in the diagram.
In this case, you do not write the associated component and mean component, but you don't assume strictness. Just omit it. You write that, right?
Right. So
You have a strict thinking of strict category.
yes, I'm assuming that we're working with a strict category.
Okay.
I think you can define this. I don't think you need to assume that it's strict. I think you can just omit all the associated unit or data in the diagrams, and they'll still work. You can prove that if the diagram, it'll like, I guess it kind of you can prove that it's like works fine. Yeah.
Okay. But I think there's no harm in assuming it's a strict category for now.
So sorry, it has strict we mean that they are called as unique space as identity. What the
So yeah, so I believe that a strict category doesn't have any isomorphisms other than the identity, and so all of these associators are just the identity.
Well, it's slightly different. So if all of your isomorphisms are equalities, then that's called skeletal, which
Okay.
definitely implies strict. But
But-
this, like, you can have isomorphisms that aren't.
Okay, so strict is
Just
just,
not apply strict. There's a different, yeah, whatever.
okay, so strict just means the associators are actually the identity. Okay, so that's all we need for now. So when we read these diagrams, just putting down two things next to each other represents the tensor product. And all morphisms are given by, if you want your objects, you sort of read across a horizontal line, right? And your diagrams that are 2D like this are all morphisms. Okay, and like I said, we're using the optimistic convention, so the domain is what we get from reading across the bottom of the diagram, and the codomain is what we get from reading across the top. Okay, and except for loosening up what's allowed to label our strings, this is going to be actually sort of pretty generally the rules for this week. That when we talk about diagrammatics and categories, this is the context for it. Okay? Okay, so a Frobenius structure is an object which is both a monoid and a comonoid. So if we have the same object with both a monoid and a comonoid structure on it, we further have one relation between these, okay, which is that these two diagrams are equal to each other, then all of this data together is called a Frobenius algebra. Simon.
Just before you look in your code.
Oh, yes, it is. Thank you. Yeah. And if I'm being really careful about these pictures, I should draw these dots just a little bit differently from these dots, because you can have this structure without having these two things being dual to each other. Now, and we haven't talked about what dual means yet. We'll get to that, but not today.
I think that I thought that for the Frobenius algebra, there's one other, maybe I'm misremembering, that you want it to be like, if you have like.
So that's often a requirement, but in fact, it's a consequence of this.
Oh, really?
You can
Cool.
prove it using the your monoid or comonoid relations.
Cool, thank you.
Is this the board that's going to move? Okay. I'll just use this one. Let's do some examples, right? Okay. There's a lot of examples, but maybe we'll start with the most basic ones. Yeah. So if H is any Hilbert space, and let's say it's a finite dimensional Hilbert space, so it has an orthonormal basis E1 through En, then to define our multiplication and our unit morphisms, we take the linear extensions of, okay, if we give this an input of EI and EJ, then what it should produce is the Kronecker delta of I and J times EI. Okay, so our multiplication here is really just comparison. If they're equal, it gives you back the thing you started with. Otherwise, it gives you nothing. Okay, so we have a comparison. And then let's have our unit here with nothing as its input, just produce the sum every basis factor. Okay. And now, what about the other kinds of maps? So if we, for our co-multiplication, if we give it EI as a basis, it's going to produce two copies of EI. So this is a copying map or cloning. And then this one can just be labeled as EI. And if you give it EI, you get the unit back. Okay, and we have some things to check, right? So-
Are we fixing or do we send every EI to one? Is that the idea?
Yes.
Okay, cool. Thank you.
Okay, so let's label this as example/exercise, and maybe we'll think about one of these in any detail, but not really the others, right? So we really should check associativity and co-associativity, right? So it's pretty easy to see that if you have to do a comparison, it kind of doesn't, if you're comparing three things to see if they're all equal, it doesn't matter what order you do the comparison in. And if you're copying something, making one thing into three copies of itself, again, it doesn't matter where you do that. So those ones, there's not really much to say. What about one of these requirements about the multiplication and the unit, right? So let's say we draw this diagram and we give it EI down here, okay? And now, as you read upwards, at some point, you read across the middle and suddenly there are two strands, right? So we have to use this. And so now this strand is labeled by everything, the sum of everything, right? But when we get to our comparison point, the only thing that survives there, it would be good to here. Let's call this J, right? The only one of these that survives is the one that's labeled EI. And so we do get EI at the top, right? And that's exactly what we'd have got if we just had the identity. Okay, so we feel good about that. And all the other versions of that we could check. And so finally, what about the Frobenius structure? Well, let's see. What if I put an EI here and an EJ here? EI here and EJ here. Okay. Maybe this is a good one to leave as an exercise, right? To actually check that whatever output we get across the top is the same for these two diagrams. Let's do, yes.
What is the hyperspace structure needed?
What's that?
Where is the hyperspace structure needed?
Where's the Hilbert space structure needed? It's not particularly used in this setup.
Can I just ask Emily for clarity?
Mhm.
This is really the tensor algebra of your Hilbert space as the example, because you need the unit and you need to be able to take tensor products and units to...
That's a good point that I don't actually have, yeah. Sure. What's the notation for that? Can I just write this?
You
Okay.
get to make up your own notation.
Sure. Yeah, that's a good point, right? That there is maybe something a little bit different about this than actually just Hilbert space.
You're drawing diagrams meant to be a Frobenius algebra, then you need to have all of these things, and she's defined these diagrams in terms of tensor product.
Okay, yeah.
You need to have a unit, for example. So,
I thought that was just code one of basically. We'll see.
but that's not an element of the Hilbert space.
No, but it doesn't kind of read that.
So you construct the tensor algebra in order to get all these things, is what I'm suggesting.
This all works in vector spaces, but like maybe the first part of the talk is related to this part of the talk. So maybe that's why we're doing multi spaces.
Yeah.
It's done because of physics, basically. Basically, you want these two elements to space of some pre-equal theory, right? You need to kill the inner product with compute transition probability. So that's why it becomes the structure.
I'm happy to come back to this at the end of the talk. I don't have a good answer off the top of my head. So, okay. Okay. For our second example, let's start with a finite group G, and let's look at its group algebra. Okay, so in other words, the elements of G are an orthonormal basis for this algebra. Okay, and so now I need to tell you again how to interpret all of these diagrams. This one should look like this, and I'm missing this. Okay, and now this one that acts like multiplication is literally just group multiplication. Okay, and the unit is supposed to give me back the identity element of my group. And now what is my co-multiplication? Okay, well, here's where, so far, right, when I write down these pictures and I label the particular strings, I mean, take the linear extension of this to define the whole thing. But here with this one, I'm not going to end up with just individual labels on the strings. I'm going to end up with something more general in the group algebra, which is the sum over all group elements, call them H, of G, H inverse, tensor H. Okay, which is the same as what we would get if we did it as H tensor H inverse G. Okay, so basically, you have a multiplication and you have a splitting, and you want it to kind of reverse multiplication in some way, but there's no, in a group, there's no good way to make that choice, right? There's no groups that have like whatever the opposite of unique factorization is, right? So we just choose, it's a finite group, and so we can just choose all of them. We can say just add together all of the different splittings you could get. Okay, and then my final diagram takes in any group element G and gives back 0 if G is not the identity, and 1 if G is the identity, right? This is a map from the group algebra to the complex numbers, and so it's the extension of this. And so, of course, we can leave this as an exercise to check the monoid and the comonoid and the Frobenius relations.
Could you clarify which category I assume about?
Okay, which category is my group algebra in? Hilbert spaces? Yeah, let's say Hilbert space.
So, well, why do we have two possible values for this morphism? So what is a good name?
So this is a map that starts with the group algebra and ends with the unit object in my category, which in this case is just the complex numbers. It's the field. Yeah, absolutely.
Yeah.
Yeah.
GH equal 0 is not in match.
Here?
You say G is the orthonormal basis.
Yeah, so G and H are any two elements of the group. So G and H in this picture are any two elements of G. And this, when you have them as labels on the strings here, they just multiply them together.
I agree with G the basis, but I didn't see why the normal and also.
Oh, it's just our definition, right? Like we start with taking, you know, the complex span of the different elements of our finite group, and then we introduce an inner product that makes them into an orthonormal basis.
How do you divide that?
What's that?
How did you divide that?
How did I?
The inner product. How do you divide the inner product make the G then?
She wants to define the inner product.
How did I define the inner product? Sure. So take the linear extension of, well, I mean, if I have some coefficients, CI GI, and another element that has coefficients, DJ, DJ, then what I want to get is the sum of CI DJ, right? So that, in other words, this is the extension of just the Kronecker delta that tells you if the two group elements are equal.
I think you need a conjugate on one of those.
Yeah, I'm working
And
on
also,
complex numbers.
and so don't you want it? I feel like you want it to be just have the coefficients match, because if they don't match, then you're going to get 0, aren't you? Because GI is, if I is
One sum of CI DI conjugate,
I want,
or if you're a proper physicist, CI conjugate.
oh, you know, you're right, that should be an I. Yes, absolutely. Thank you. But the conjugate is right.
Should be on the other one.
It should be on the other one. The conjugate is fine. Okay, good. What else?
The inner product follows from the other structures of Frobenius algebra, right? From taking product and then taking the co-unit. No?
I think so, but I'm not 100% sure. But and then I'm going to give you a third example in much less detail than the examples that I've already given you, okay? Which is that, in particular, if you've encountered a Hopf algebra before, a Hopf algebra is an example of a Frobenius algebra, okay? So, in fact, before I gave this talk, I got myself confused and I sat down and I Googled what is the difference between a Frobenius algebra and Hopf algebra, and the difference is that a Frobenius algebra is a general notion in any monoidal category, right? And Hopf algebras exist in more specific contexts. Okay, but if you, and in fact, probably I need to specify that any finite dimensional Hopf algebra is a Frobenius algebra. Okay, that's all I want to say about that, but I would be remiss if I didn't mention that.
So I just wanted to add one thing. So it's important to mention in the third example, Hopf algebra also comes with a coproduct, but the Frobenius algebra structure has a different coproduct than the one that the Hopf algebra comes with.
Okay.
Yeah.
That's an excellent thing to mention. Thank you for saying that.
Product algebra. It's not true for Frobenius algebra.
Okay.
I think the difference is
I would-
that the co-product for Hopf algebra is an algebra match in some subset, and for Frobenius algebra it's a Feynman. So in both cases, the co-product is compatible with the algebra structure, but in two different ways. In the two natural ways.
Okay. I would love to get this cleared up, but I also only have 12 minutes left. So yes, please stay and tell me more about Hopf algebras after this talk, okay? Okay, great. So now we get to have move on to part 3 of this talk, which is what do Frobenius algebras and TQFTs have to do with each other? Let's say we have a two-dimensional topological quantum field theory. We'll call it A. Okay, and now let's think a little bit about the category of two cobordisms. Okay, so we have closed compact one manifolds oriented. Okay, in other words, circles, right? All we have here is circles. We might have a lot of them, but our circles are a building block here. Okay, so the interesting things in the category of two cobordisms are the morphisms. Okay, and so in particular, the set of objects of this category is tensor generated by the image on a single circle, right? And if we want to know what's happening on, if we have a TQFT and we know what it does to a single circle, then by using the fact that it's a monoidal functor, we know what it does to any object. And so to understand the TQFT, the image of the circle is the main object. It's a very technical term in category theory, right? The main object. Okay, but in particular, this most interesting object here is a Frobenius algebra. Okay, and I should give myself more room for this. There's not much point in drawing nice pictures that are too small to see. So if I think about what does my TQFDT do to the cobordism, which is a pair of pants? Well, then it takes two circles into one circle, right? And what does my TQFDT do to the morphism, which is it's either a hemisphere or really just a disk, right? Well, so now this is a map that takes my unit into the image of the circle. Okay, I don't need to painfully write down these domains and codomains, right? But we also have upside down pants, and we have a cup, right? And so we get the ingredients we need to have a Frobenius structure if we can check that the conditions hold. Okay, and so then the relations we have to check are, let's see, we have associativity, so pants, and then a cylinder, and another pair of pants, right? And if we're thinking of this as a surface, right, a two-dimensional surface in 3 space, then I'm going to erase this thing where we've done the gluing, and now we can just kind of slide this joint up to the middle and keep sliding and just do the topological deformation to end up back here with this. Okay, and so all of the relations you expect hold when you're thinking about all of the Frobenius relations are true for surfaces just by doing these, what are they called? Isotopies. Okay, so skipping the unit map, right? The Frobenius condition is that we combine pants and upside down pants in the 2 different ways. We should get equal things. And okay, so it's pretty easy to see that these are equal to each other just by kind of sliding everything to the middle and noticing that topologically this surface is the same as a surface that looks like this. Okay, and so in particular, if we ever have a TQFT, we get a Frobenius algebra from it. Okay, and so that's that's the punchline. All right, I'm done for today.
Okay, do you have questions? Yeah.
So I guess maybe this is probably best to talk to you afterwards, but I guess I thought that, as I said, like, to feel like the thing that you have, that thing that you have for the topological things, that sort of thing, feel like should hold generally for Frobenius algebras, right?
It does.
So yeah, I guess I'm a little bit unsure how you would necessarily show that if you happen to know.
I don't have that off the top of my head.
Sure.
But on the other hand, I also think if you just
is it something that you can do just graphically?
Yes, you can.
Okay.
It's in the Kunin and Vickery book.
Okay. Thank you.
The motivation for Frobenius relations come from this example, or it was introduced separately?
I think that Frobenius algebras are older than quantum field theories, right? So I think that this is actually a sort of older concept in algebra, and that sort of I'm using this as a motivation because it's one that I can understand. But I think that sort of Frobenius algebras are interesting on a purely algebraic level as well as in this way.
Okay.
So just one addition, I think in that theorem, it's a bijection between TQFTs and Frobenius algebras, like not just one direction.
Yeah, I don't think there's a bijection necessarily between TQFTs and Frobenius algebras, but I think that a 2D TQFT gives you a Frobenius algebra. Now, these are symmetric Frobenius algebras. Okay, because of the topological nature, if you added in a twist, right? So this leg comes in front and this leg is behind, that this would just be the same thing you're starting with, but there's no commutativity requirement for Frobenius algebras. So there are some Frobenius algebras that don't arise
Right.
from
So
TQFTs.
I meant like when you define TQFT, you just defined as a monoidal functor. So if that's the definition of TQFT, then you get a bijection with Frobenius algebras. If you say that a TQFT is a symmetric monoidal functor, then it becomes a bijection with commutative Frobenius algebras.
Okay.
I think so.
Okay.
Yeah, I might be wrong.
Okay,
Yeah, I think you always get a symmetric Frobenius algebra. Even if you don't require it to be a symmetric monoidal functor, that you always get a symmetric Frobenius algebra.
Thank you. Any other comments? So if not, we thank Millie again. So it's the end of the day. It's the end of the day. And there will be a coffee break within half an hour.